Okay, so this is where we are with exoplanet atmospheres in the 2020s. It's going to be a sort of potted summary. So the way in which we are able to observe atmospheres has evolved quite a bit since the textbook you work from was written. One of the major methods of doing this is still transit spectroscopy, which is something that is covered in S382, but the technique is now much further advanced, and we are able to obtain far more information than is described within the original course content. We've also been able to do much more in terms of looking at planetary atmospheres when the planet is eclipsed by the star, and also to monitor the atmospheric signal as a function of phase. So as the planet goes through a single orbit, we see different sides of the planet rotating into view, and we've been able to get some really very precise measurements of some of the phase curves as well. Some other techniques that weren't really covered at all in the course that have become important are Doppler spectroscopy, which is something that's developed much more recently. It has some similarities with the radial velocity technique that you'd be familiar with for measuring the planet mass. And also our ability to obtain spectra of planets directly has come quite a long way for certain classes of exoplanet. So for the first bit of this talk, I'm going to go through these three methods that we use to observe atmospheres and just give you a rough introduction to each one of those. So transit spectroscopy is the one that you're already familiar with. This is just a recap. So as the planet transits its parent star, it blocks some of the starlight. The bit of the planet in the middle, whether it's a solid lump of rock or simply a very dense region of gas that's dense enough such that light can't get through at any wavelength, that blocks out the starlight at all wavelengths, but the atmosphere is transparent to some wavelengths of light and opaque in others, depending on the gases that are present within the atmosphere. So in this toy example, the gas that I've chosen is sodium. So this exoplanet has sodium in its atmosphere. So light on either side of the sodium absorption band, that gets straight through the atmosphere, but the sodium band absorbs the light of that particular wavelength. And what this translates to in practice is an apparently larger planet if we view it just in that sodium absorption band. So we see a deeper transit depth because more of the starlight is being blocked. And this, of course, extends to absorption by any atmospheric constituent. It doesn't have to just be sodium. As you go further into the infrared, you start to see absorption signatures from molecules, so things like water vapor, methane, carbon dioxide. So when the planet goes behind the star, at the opposite phase in its orbit, then we can also measure the contribution of light that's actually emerging from the planet itself. So when the planet is eclipsed, we see a dip in the total amount of light coming from the system. This time it doesn't correspond to the starlight that's being blocked, it corresponds to the light from the planet that's being lost entirely. And broadly speaking, you see a deeper eclipse as you look at longer wavelengths of light, because the planet is cooler than the star, so its black body peaks at longer wavelengths compared with the star. So you get a better contrast as you go further into the infrared. So that's a broad trend. You still also get bumps and wiggles in your spectrum due to absorption from various molecules, just as in the same way as you do in transit. And as well as observing during transit and during eclipse, we are now also able to observe phase curves for some targets very well, and also spectroscopically, which certainly wasn't possible when this course was written. So what that simply means is, rather than just observing the transit or eclipse, we monitor the brightness of the star and planet combined throughout a full orbit of the planet. This is doable for many transiting planets because their orbits are quite short, of order only a few days. And as we measure the change in the amount of flux coming from the system, what we're seeing is the bright side, the day side of the planet rotating into view and then rotating out of view again. And we're also able to look at the distribution of where the radiation's coming from on the planet. So from looking at phase curves, we've learned that actually the brightest part of the planet for the majority of the hot Jupiter transiting planets we know of is not actually the bit directly beneath the star. It's slightly offset from that. And from that we can infer that there are very, very strong winds within the atmosphere of the planet that's actually pulling that hottest bit of the atmosphere away from the bit directly beneath the star. So just to give you an idea of how the observations themselves have advanced, on the left-hand side, this is one of the very early transmission spectra of a planet called HD 189733b. And if I'm perfectly honest, calling this a spectrum at all is very, very generous. It's 3 photometry points. And yes, you could argue that they look a bit like what is in this case a water vapor absorption feature. So at 6 microns, you've got more absorption due to under 4 microns. As it happens, the interpretation of this measurement is probably correct. We do know that there is water on this planet now, but at the time it was probably actually a bit tenuous. On the right hand side, we've got a much more recent example of a transmission spectrum for an exoplanet. So you can immediately see that the wavelength coverage we're able to achieve has improved enormously. We are now able to get really quite comprehensive coverage from the near ultraviolet through to the near infrared. We generally do this using the Hubble Space Telescope. The 2 instruments are STIS, which is the one that goes up to just shy of 0.9 microns, and the Wide Field Camera 3 instrument, which continues beyond that. The 2 individual points off to the right there are from the Spitzer spacecraft, which is sadly now decommissioned. But as I'll mention later on, the infrared is going to be taken over by the James Webb Space Telescope when it launches later this year. So we will get much better spectra in the infrared going forward. So the black points are the actual measurements, and the red line is our best fitting model for that particular planet. The blue envelopes correspond to the 1 sigma and 2 sigma error bars on that best fitting model. And you can see that we've got we can see very clearly absorption due to sodium, absorption due to potassium, that's K, and also several bumps that are due to water vapor. Eclipse spectra, again, we've had similar levels of advance. So on the left-hand side, you've got a very early eclipse spectrum. Again, it's only a handful of spectral points. On the right-hand side, we've got a much more comprehensive spectrum. This is, again, actually for HD 189733b, which is one of the best studied exoplanets we know of so far. And you can see, as I explained before, that that the ratio of the planet flux to the star flux increases as you go to longer wavelengths from left to right, because the planet's cooler, so the Planck function is peaking at longer wavelengths. But you can also see the bumps and wiggles that correspond to absorption from different gases. And finally, phase curves. So again, we've got HD 189733b on the left-hand side. So this is one of the earlier phase curves. This was observed with Spitzer. So we've got just 4 different wavelengths. And then on the right-hand side, we've got a later phase curve observation of a planet called WASP 43b. These are all hot Jupiters so far that I've been referring to. And this was done with the Wide Field Camera 3 instrument on Hubble. So you can see we get a much broader range of wavelengths. And what we're able to see is the change in absorption strength for the water vapor absorption feature as a function of phase. So we actually get some information about changes in the chemistry of the atmosphere as a function of phase. So that's sort of where we've got to so far with the transit eclipse phase curve technique. Now I want to talk a little bit about how Doppler spectroscopy works. So this is very, very similar in many ways to the radial velocity technique for detecting a planet, but whereas in that case what we rely on is the spectrum of the star, here what we're actually trying to tease out is the spectrum of the planet itself. This is a particularly valuable technique because it doesn't require the planet to be transiting, although it requires the inclination to be not too far away from 90 degrees so that we still get a substantial radial velocity signature. So the way that this works is we use a high-resolution spectrograph of the same type we would use to detect planets using radial velocities. And because we've already found the planet, we know what its orbit ought to be doing. So we know what the radial velocity signature of the planet ought to be. So what we do is we produce a template spectrum containing absorption features for whatever we're interested in finding in the atmosphere. So as an example, it could be carbon monoxide. So we'd produce a very accurate, very high resolution template absorption spectrum from carbon monoxide. And then what we'd do is cross-correlate that template with the measured spectrum as the planet moves towards us and away from us. And because we know how fast the planet ought to be moving during its orbit, then we can disentangle the contribution from the planet from carbon monoxide absorption either in the star or within our own atmosphere. So in the previous example, you could see that the template spectrum was never going to match up with the measured spectrum, but in this example, at some points in the planet's orbit, you're going to get a positive correlation. You're going to see that the measured spectrum matches up with the template spectrum. Of course, in reality, the measured spectrum would look a whole lot more messy because there'd be absorption from lots of different things. But this is just an idealized view, so you can see roughly how it works. And this is actually a set of results using that method. So if you look at the slightly smaller figures, so on the right-hand side of each column, this is a cross-correlation plot. So where you see the bright white region, that's where the correlation peaks. And the two axes are the system velocity on the bottom, so that's how fast the entire planet-star system is moving away from us or towards us. In this case, it's moving towards us. It's slightly blue shifted. And then on the y-axis, you've got the radial velocity of the planet itself. So using this technique, and for this particular planet, which is called Kelt 9b, it's what one of the planets we call an ultra-hot Jupiter, so it has an equilibrium temperature that's well over 2,500 Kelvin, so extremely hot. And actually, because it's so hot, you start to see the sorts of chemistry in the atmosphere that we see in some stars. So rather than seeing lots of molecular species, you've got ionized metals, things like scandium-2. So we're able to use this technique to very good effect, particularly to see some of these species that absorb in the optical. And finally, the prospects for direct imaging have really improved over the last 10 years or so, mainly due to advances in instrumentation and techniques. So this technique works for a very different subset of planets to the ones that I've spoken about so far. So we're still talking about hot planets, we're still talking about Jupiter-sized planets, but they're not what we call hot Jupiters. These instead are young planets that are hot because they're young, because there's still lots of heat left over from their formation, and they're much more distant from their parent stars. So we're talking about separations of several tens of astronomical units, rather than a few percent of one astronomical unit, which is more typical for a hot Jupiter. So what we need to achieve here is two things. We need to maximize the spatial resolution so that we can well separate the signals from the star and the planet. And ideally, what we also would like to do is just get rid of the contribution from the star full stop, because the star just gets in the way. It's much, much brighter than the planet, and if we're not careful, it's going to overwhelm the planet's signal so that we can't identify it. So there are a number of techniques that we can bring to bear on this problem. So one technique that's quite successful at actually getting rid of the contribution from the star is something called coronography. So this is one example of how this can be done. This is the LEO coronagraph in this example. And so the way it works is the light comes into your telescope, into your optical system. It's brought to a focus, and at this point the planet is present, but it's overwhelmed by the light coming from the central star, which is marked in the bottom set of diagrams by a cross. Now, as part of the telescope optics, there's then a physical spot in the center of your focus, in the center of your image, and that blocks the light from the center, so that blocks the starlight out. You then pass that through another lens, and then what you're left with is something with the starlight from the middle blocked out, but because you've put a physical stop in with sharp edges, you've got some light that diffracts around the edge of that physical stop. So you need to remove some of those fringes too. So that's where this next bit comes in. This is called the Leo stop. So this is another physical stop within your optical path, but this one gets rid of the diffracted light. And then you bring your light to a focus again at the detector. You've still got some contamination from the star. You can't remove the starlight entirely, but the planet, which actually isn't very visible on your screen, I'm sorry, there is a red dot in there. The planet then becomes visible, so you can remove the starlight using that sort of technique. In terms of maximizing our ability to resolve small features, there are a couple of things we need to consider. So one technique that's been really very useful is something called adaptive optics. So in an ideal world, the atmosphere would not affect the incoming light to our telescope at all, but of course in reality we know that it does. Our atmosphere is by nature not homogeneous. It's not the same everywhere. There'll be some bits that are slightly wetter than others. There'll be some bits that are slightly warmer than others. And what that does, if you imagine your light coming in as a series of wavefronts straight and parallel above the atmosphere, once they've passed through the atmosphere, they've got a ton of wiggles in because the atmosphere isn't perfect. So if you imagine what happens when that intersects with your telescope, it means that on each little bit of your telescope mirror, the light is impacting at a very slightly different angle, and that contributes to making your image fuzzier than it should otherwise be. So what you can do is engineer a telescope that can react to this in real time. So if you've got a perturbed wavefront, it's coming in, you can have a little array of tiny lenses. If you had a perfect wavefront, that little array of lenses would produce an image exactly within the center of each lens, but because the wavefront is coming in at an angle, the image that each lenslet produces is offset by a certain distance. So if we have a detector that can measure the offset, then we've got some information about what the wavefront is doing. So that's the first part of this. We need to have the information about what the wavefront is doing. The second aspect of this is we have a telescope mirror that can actually change its shape to compensate for that effect. So this is an image of just such a mirror. I don't know if you can see on your screen, but there are some sort of ripple shapes on that mirror. That's actually the mirror having deformed to take into account the wavefront shift. And to give you an idea of just how successful this is an image of Neptune, I believe. So on the left-hand side, you've got the adaptive optics case. The right-hand side is what you would get if you weren't employing adaptive optics. So you can see the image on the right-hand side is very, very poorly defined. It's extremely fuzzy. Using adaptive optics allows you to access a much greater level of detail. And finally, one of the techniques we can use, which is simply to improve the angular resolution of a telescope, is interferometry. So the angular resolution of a telescope, assuming no interference from the atmosphere, is approximately equal to the wavelength of the light you're using to do the observation divided by the diameter of the telescope. But if you want to, you can combine light from multiple telescopes to make a sort of pseudo telescope, and in that instance the d in the denominator of that equation becomes the maximum distance between any two telescopes in the array. So this works if we can ensure that the light coming to each telescope constructively interferes, so the light has to be in phase with for each telescope. So all of these techniques together have been used over the last few years to improve our ability to observe exoplanets directly. So this is how much progress we've made. On the left-hand side is a spectrum of a planet called HR8799b. This is a young Jupiter-type planet where we've got a handful of spectral points and maybe a very tentative detection of methane. On the right-hand side is a spectrum obtained using an instrument called the Gemini Planet Imager. And this is a spectrum of a planet called 51 Eridani b. This is a particularly interesting target because it's often referred to as a sort of young or teenage Jupiter. It's a Jupiter, roughly Jupiter mass planet, and it has very, very deep absorption features that are due to methane. So the shape of that spectrum is being almost entirely sculpted by methane. Because of the amount of methane in its atmosphere, we think that once it cools down, it's quite likely to end up looking a lot like Jupiter in the solar system. So those are the techniques that we're currently using to look at planets' atmospheres. But what are we actually trying to achieve here? Well, in an ideal world, which this world is not ideal, so we're not going to get this. What we would like to be able to do is to eventually classify planets in much the same way as we classify stars. So this is, of course, the HR diagram, and it's a very, very neat way of classifying stellar objects. Planets, on the other hand, are the reason for that, in part, is that they don't exist in isolation. You don't get very often a planet without a star. So it's not just the characteristics of the planet itself we have to take into account here. We also need to account for the influence of the star, and that makes things much more complex. But this is a sort of a conceptual diagram of what we might be trying to get to in terms of categorizing planets, and we're really not there yet. We've got a long way to go still. So this diagram uses planet mass and equilibrium temperature for the axes, and I'm just going to populate it with the solar system planets to give you a bit of an idea of where different planets would lie on this diagram. So in the top left we've got the common or garden coolish gas giant planets that are dominated by hydrogen and helium, molecular hydrogen and helium. If you took those planets and heated them up quite a lot, so up to the temperature of some of those ultra-hot Jupiters I mentioned earlier, then the hydrogen would dissociate and you'd end up with something made of atomic hydrogen and helium, so just one hydrogen on its own. So those are the gas giants, and give or take, they're all pretty much going to be hydrogen-helium mixtures, simply because to make a big thing you need lots of stuff, and what's the most abundant stuff? Hydrogen and helium. What's a little more interesting is this region in the middle of the plot, which is where we find planets like the Earth and Venus and Mars. So these are terrestrial planets. So Venus sits just to the right-hand side of a red dotted line that's labelled H2O runaway greenhouse. So what that line indicates is the temperature beyond which you wouldn't be able to maintain liquid water on the surface, because any water that was a liquid on the surface would evaporate. It would then contribute to the greenhouse effect of the atmosphere, which would evaporate even more water, which would make it hotter, and so on and so forth, until all of your liquid water is evaporated, it's in the atmosphere, and eventually the planet will be so hot that the water would start to dissociate, to pull apart. And then once that happens, the hydrogen is very readily lost into space, and that's it. There's no going back from that situation. So planets to the right-hand side, in hotter regions of that diagram, will end up with atmospheres dominated by things like carbon dioxide or carbon monoxide and nitrogen, which is pretty much what Venus's atmosphere is made of. If you're on the right, if you're at the right, or rather the left, but the correct side of that line, if you like, then you get something like the Earth. So a planet that's able to maintain liquid water. In the Earth's case, it's not so cold that the water would become ice. What you would expect a priori for a planet like this is to have a mixture of carbon monoxide or dioxide, probably more likely carbon dioxide, nitrogen and water vapor. Of course, what we have is an atmosphere dominated by nitrogen and oxygen. We know why the oxygen is there. It's because of life. The reason that we don't have a huge amount of CO2 is because of weathering. So the carbon silicate cycle draws down carbon from the atmosphere and locks it away in rocks. And that's also a consequence of the fact that we have a liquid water ocean. Mars exists sort of on the left-hand side of this little chunk of the diagram. So Mars has an atmosphere that's dominated by CO2 and nitrogen. If Mars was any colder, then it would be on the wrong side of the blue line, which is marked CO2 collapse. So this would be where CO2 freezes out of the atmosphere because it's so cold. So Saturn's moon Titan, if it was on the diagram, would actually sit somewhere over to the left there. And then finally, at the very bottom, you've got the tenuous atmospheres. So this is the case where the planet's either too small or too hot, or both, to be able to maintain a substantial atmosphere long term. And Mercury, unfortunately for Mercury, sits down there. So what are the things that we need to learn about the planets in order to categorize them in that way? Well, we need to learn about the atmospheric structure. We need to learn about its composition. We'd like to know about its dynamics. How does the atmosphere change? How does the atmosphere circulate? And we'd also like to know about any aerosols, any clouds within the atmosphere. So how do we go about learning this? Well, this is an example of atmospheric structure. So this is thermal structure of our atmosphere, the Earth's atmosphere. It's split up into 4 different regions. So at the very bottom is the troposphere. That's the bit of the atmosphere that we're most familiar with. It's where the majority of weather systems occur. It's where the clouds form that we can see. And it's convective. So heat transport in this region of the atmosphere operates via convection. On top of that, you'll see that the temperature starts to increase again as a function of altitude. We call this region the stratosphere. So in this region, the atmosphere is thermally stable to disturbance, so you don't get any convection. Energy instead is lost to space through radiation. The reason that you get that turnover, you get that increase in temperature again, is because of ozone. So our ozone layer sits about 10 kilometers up in the atmosphere, and it readily absorbs ultraviolet photons from the sun. That's a source of energy. And then it re-radiates that energy in the infrared, and in doing so, it heats up that region of the atmosphere above the ozone layer. Then above that, we have another turnover. The temperature starts to decrease again as you go further up. This is the bit we call the mesosphere, which literally just means the middle of the atmosphere. This is where sort of large-scale waves and dynamical features occur. And then finally, at the very top, we have a region called the thermosphere, and that's the highest region of our atmosphere that's coherent. Up here, the gas is largely ionized because there's some contact with cosmic rays and the solar wind. So how typical is this sort of structure? Well, one of the things that we can infer just from looking at our own solar system is that a key discriminator of different types of atmosphere is whether or not you have a stratosphere, whether or not you have this turnover where the temperature starts to increase again as a function of altitude. So the giant planets in our solar system all do have stratospheres, and that's because they have methane in their atmospheres, which absorbs quite readily at short wavelengths. So the methane on the giant planets serves much the same function as ozone does in our atmosphere. On the other hand, Venus and Mars do not have a stratosphere. There is no absorber in the UV and optical that absorbs sufficiently to heat up that part of the atmosphere. So that's something that we're interested in looking at for exoplanets. Does the planet have a stratosphere or not? Of course, we're also interested in the composition, and different gases will absorb at different wavelengths. That provides us with a key to composition. This is again an example using Venus, Earth and Mars. So the spectrum on the top is Venus, then Earth in the middle, Mars at the bottom. You can see that they all have one feature in common, and that's absorption due to carbon dioxide, because all 3 planets have carbon dioxide in their atmospheres. Earth's looks quite different to the other 2 because we have absorption from water vapor. That's what produces the very jagged sort of comb-like features. And you've got the ozone absorption as well, just in the middle of that. Varying amounts of absorption at different wavelengths in the atmosphere it affects where in the atmosphere you're seeing radiation from at each wavelength. So spectroscopy can also be a key not just to composition but also to determining the atmospheric structure and looking at temperature as a function of pressure. So this is a little toy example, but it's actually quite a good one. So I'm showing you another spectrum here of the Earth. This is a real spectrum of Earth's atmosphere. It's a bit backwards perhaps from your point of view, so wavelength is increasing from right to left here. And the spectrum itself is the black solid line. What you'll notice is that you've got a series of dashed curves on top of that, and these correspond to Planck functions at a range of different temperatures. So 280 Kelvin at the top to 220 Kelvin at the bottom. We can identify three different regions in that spectrum where the conditions are somewhat different. So in the region that's highlighted in red in the middle, this is what we call an atmospheric window region. So there's no absorption in this region, no gases present that would absorb. So the atmosphere is pretty much completely transparent. And what that means is that any radiation escaping out into space is actually coming all the way from the surface of the planet. The opposite case is the blue region. So the blue region is in the middle of an absorption band of CO2. Now, this particular absorption band of CO2 at 15 microns in the infrared is what we call saturated. That means that even if we put more CO2 into the atmosphere, you're not going to get any more absorption because it's already absorbing as much radiation as there is. So in this particular band, the atmosphere is completely opaque. Nothing is escaping from the surface of the planet at all. The only radiation that's emerging is actually coming from the top of the atmosphere itself. And then you've got the ozone band to the right-hand side that's shaded in yellow, and this is a halfway case. The atmosphere is partially transparent here. So we can actually construct a very crude model of the temperature structure of the lower bit of Earth's atmosphere, the troposphere, just based on looking at this plot. Because what we can see is that in the window region, the spectrum is pretty much on top of the 280 Kelvin Planck function. So that means the planet's emitting at about 280 Kelvin. We know that there's no absorption there. Everything that's coming out is coming from the surface. So we can infer from that that the surface temperature of the planet is 280 Kelvin. If we then look at the CO2 band, we know that the atmosphere is opaque here, so that what we're seeing is coming from the top of the atmosphere. And by atmosphere, I mean the troposphere, I mean the bottom bit of the atmosphere. So that tells us that the temperature of the troposphere, at the top of the troposphere, is 220 Kelvin, because in that region, the spectrum is lying on top of the 220 Kelvin Planck function. And again, for the ozone case, it's somewhere in between. So just looking at a diagram like this, we can construct a very crude temperature profile that says at the bottom, it's 280 Kelvin, and it decreases down to 220 Kelvin at the top of the troposphere. So obviously when we do this in real life, we don't just look at a diagram like this, we do something a little more sophisticated. What we do is we apply a series of atmospheric models and try and get them to match what we observe. But the process is actually effectively the same. So this is what we would actually do. This is a toy example of spectral inversion, and this is what I spend most of my time doing during the research part of my job. So we have an observation. This is an example of a transit observation, and we have a basic model atmosphere set up on the computer. We can generate a number of different flavors of that atmosphere with slightly different temperature structures, slightly different compositions. We simulate the passage of starlight through each of those atmospheres and generate a spectrum that we would expect to see. And then what we do is we just compare it with the observation. In this toy model, I think everybody can see that it's the green flavored atmosphere that produces a spectrum that matches the observation. In reality, you don't usually get such a nice clear-cut answer. You'll get a family of different model atmospheres that all do a reasonable job of fitting your spectrum. So you don't get one single absolutely true answer, you get a statistical range of possibilities. So this is an example of some results from just that process. So this is another hot Jupiter observed in transit. So this is the transit depth you can see on the left hand side. So where you've got larger transit depth, that's where you've got more absorption. So the feature sort of over to the right, that very clearly defined bump, that's water vapour. And we've applied a series of model fits here, and what we have got out are some statistical probability distributions for the various properties we've put into our model. So if you look at the top square in the column that's marked H2O, then we've used two different computer models to do this, and you've got two different curves that basically say how likely is it that there's this much water vapour in the atmosphere. So where you've got the peak, that's the most likely value, but you've also got a spread of values that are quite possible as well. Right, so I've got a video to show you here. So this is for another hot Jupiter, WASP 43b, and this is a video of a planet where we've actually been able to observe the phase curve spectroscopically. So this is really very, very neat. So you can see that from observing the phase curve at different wavelengths, we're able to extract a spectrum at each phase, and we're able to extract the thermal profile at each phase. So the diagram in the top right is how the temperature varies as a function of pressure. A map of the planet for each wavelength. So this is really getting to the cutting edge of what we're able to do at the moment, is to produce something this comprehensive. So what have we actually found out so far using this sort of technique? Well, we've got a vast number of observations of hot Jupiters, which is really quite useful. Some of them we have a really broad spectral range going from that near ultraviolet part of the spectrum right through to the infrared. Some of them we've just got a little chunk of spectrum in the infrared. So for the ones where we've just got a little bit of spectrum, we can make some pronouncements about how much water vapour we see, but probably can't say very much else. If you look at the series of spectra that I'm showing on the right-hand side here, these are the more comprehensive observations. So I've highlighted the absorption due to sodium, that's the yellow band, potassium, which is the more orangey band, and then water vapour as you go into the infrared. You can see that, broadly speaking, the shape of the spectrum is the same throughout, but also I think you'd agree that there are different slopes going from the optical through to the infrared, and we think that that's a consequence of differences in the cloud properties on these planets. And you can also see that the size of the absorption features varies quite a lot for the different planets. So we're actually getting to the point where we can start to draw comparisons between these planets, which is certainly not where we were 10 years ago. One of the things that's quite interesting for me that has emerged from this process is that water is pretty much everywhere, even on hot Jupiters, which might come as a surprise to you, because you tend to associate water, I think, with cooler objects. But actually, no, water vapour is everywhere in these atmospheres. But it's consistently below what we would expect for if we assume that the star is a solar metallicity star. So if we take an atmosphere that's sort of got a roughly solar metallicity composition and we heat it up to the planets, then the amount of water that we would expect to see from that process is quite significantly higher than the amount of water vapour we actually do see. We don't know if that's real or not. It's certainly something that is robust as a result. We see it recurring again and again. What we don't know is whether that indicates a real effect or something that we're doing consistently wrongly in our interpretation of the observations. So that's something that we hope to resolve over the next few years. We've also seen plenty of surprises, things that shouldn't be there that are there. So I was lucky enough to work on a paper last year on a planet called HAT-P 41b. This is another fairly average hot Jupiter. It's not an ultra hot Jupiter by any means. Its temperature is about 1500 Kelvin. And what you're seeing here is the observation, which is the black points, the model spectrum, which is in pale green, and then underneath that is a breakdown of the contributions from the different chemical components that went into the model. And the black curve at the very bottom is absorption from something called H-. This is ionized atomic hydrogen. Actually, it's an absorption feature that's produced by the interaction of atomic hydrogen with free electrons. You have to have quite a lot of free electrons to see this feature. And you would only really expect that to happen if you've got a very hot atmosphere, where the temperature is such that you'd start to strip electrons away from things. So the fact that we apparently see this is really, really weird for this planet. It's just not hot enough. So we need to think about what another source might be that would provide enough free electrons for us to see this. I talked about temperature inversions a lot a few slides ago. And indeed, one of the interesting things that we're seeing from looking at hot Jupiters is a progression as we go to higher temperature hot Jupiters, from the case where we don't see a temperature inversion, we don't see a bit of the atmosphere where the temperature increases with altitude, to a regime where we do see this happening. And we think that that's due to the presence of particular gases within the atmosphere that are condensed for the cooler planets. So they're locked away in the deep atmosphere, but then are in gas form in the warmer planets and are able to absorb. So we think that these are titanium and vanadium oxide. That's been predicted for a number of years. So the prediction is the plot on the left-hand side. These plots were generated using a series of atmospheric models about 13 years ago now. And then last year, the plot on the right-hand side was published, and what this is showing is, as a function of temperature, so going from left to right, it's getting hotter, it's showing the deviation of the spectrum from a black body. So the deviation is negative if you've got a profile that's not inverted, that doesn't turn over. It's positive if you have a profile that is inverted and turns over. There's a lot of scatter from different planets, so there's obviously quite a lot of variability between planets. But I think you can argue that at some point, at about perhaps 1700 Kelvin, you start to see a transition between the non-inverted regime and the inverted regime. So we're starting to see some of these predictions actually borne out by observations. So I've talked a lot about Jupiters, and the reason I've talked a lot about Jupiters is because they're by far the easiest planets to observe, because they're big. But we're starting to get to the point of being able to observe the atmospheres of smaller planets too. So one really nice example of this is a planet called WASP 107b, and this is a Neptune. This is a hot Neptune. And one of the really exciting recent observations, again something that was predicted a really long time ago in exoplanet science anyway, which is quite a young field, is the escape of an atmosphere from a planet that's quite small. Well, it's a Neptune-sized planet rather than a hot Jupiter. It's being very highly irradiated, so the atmosphere is actually being lost gradually to space. And we see that in this helium absorption feature, which you can see sticks out way, way, way above the rest of the spectrum. So it's this blue point. And that was observed for the first time about 3 years ago. We can also start to look at mini-Neptunes. These have perhaps been the most frustrating class of planets that we've been able to look at, because these are a really fascinating object. We don't have anything in our solar system that occupies the parameter space between a Neptune-sized thing and an Earth-sized thing. So mini-Neptunes, things that are a little bit smaller than Neptune, and super-Earths, things that are a little bit bigger than Earth, are really fascinating to us, because what we really want to uncover is where the transition occurs between a rocky thing, a large rocky thing, and a small gas giant thing. So these planets are, or should be, an absolute goldmine for information if we're able to obtain their spectra. The real problem that we have is they're all cloudy. Every single one, pretty much, that we've been able to get a spectrum of has got a totally flat spectrum. And these must have atmospheres, these planets. They are not dense enough to be bare lumps of rock. We know they're gaseous, so they should have atmospheric absorption signatures. And the only explanation for them not having signatures is that they're so cloudy that you just can't see anything. The cloud washes out everything else that we might be able to see. And that's really unfortunate and really frustrating. We're hoping that with future telescopes coming online, we might be able to beat this either by going to different wavelengths where the cloud should be less absorbing, or by going to higher resolution, which might allow us to see the narrow cores of some features just poking up above the cloud. And finally, to super-Earths. So these are planets that are up to maybe twice the radius of Earth. The one that's been studied most comprehensively is called 55 Cancri E, and this is an ultra-hot super-Earth. So this is a planet with a temperature of about 2000 Kelvin, which likely means it's a lump of molten rock. It has a molten lava surface. And there have been some tentative attempts to detect an atmosphere on this planet. An atmosphere is also being detected on a similar sized world that's somewhat cooler called GJ1132b. But you can see that for these objects we're really starting to push the limits of what we can do. I think just by comparing those with some of the spectra I showed you earlier, you can appreciate just how much better we can do for Jupiters. So we're really getting to the point where we can say a little bit about these objects, but not a huge amount as yet. And not to neglect direct imaging altogether, this was a particularly lovely example that was published last year of a directly imaged planet. This is HR8799e, of 4 young Jupiter planets. And the particularly beautiful spectrum is the one on the bottom. This is from an instrument called Gravity. This is an interferometric instrument on the Very Large Telescope in Chile. And the precision of this is absolutely exquisite for a directly imaged planet. And from this observation, some really good evidence for this planet being cloudy was produced, and some of the characteristics of the cloud were pinned down as well. What can also be done for some brown dwarf type objects, which are fairly similar to some of these young giant planets, if they're rotating fast enough, is to actually use a Doppler mapping technique to look at patchy clouds across the surface. And this was done a few years ago for an object called Lumen 16b. So we're really starting to learn a lot more about these directly imaged worlds as well. So I've reproduced my own version of the sort of planet HR diagram that I showed you earlier. We've got mass on the y-axis and temperature on the x-axis. And this is sort of what we know so far, based on everything that we've seen. So I should note that everything in the cold category is what we know from the solar system, because we don't really have any observations of exoplanets in that region as yet. So for the very, very, very hot Jupiters, the ultra-hots, we've got things like H- and other ionic species. We've got metal oxides and temperature inversions. For the more standard hot Jupiters, we see water vapor, but less than we expect. More CO than methane, some silicate clouds, a few surprises like the H- on HAT-P41b that we don't think should be there. Going down to the slightly warmer, there's the warm objects rather than the hot objects, particularly the Neptunes. We've got evidence of escaping atmospheres. We've got missing methane on these planets. We expect there to be methane and there isn't. Getting down to the mini Neptunes, we've got just clouds, which is really frustrating. For the one sort of data point we've got for an ultra-hot super-Earth, we've got maybe a silica atmosphere or maybe something entirely different. And you can see there's loads of question marks on this diagram. Some of the question marks, particularly the one up here, it's not due to a lack of ability to observe targets we know of, it's actually due to a lack of targets. So I think Carol mentioned in her lecture last week the presence of a Neptune desert where we just don't have as many objects occupying that parameter space. But for the cases where we do have targets, this is what we expect to be our silver bullet. This is the James Webb Space Telescope, and we think this is going to transform our ability to characterize exoplanet atmospheres. So James Webb is particularly special because it allows us to probe the spectrum from the very red end of the visible right through to the mid-infrared. And the mode that's particularly useful for exoplanets, for transiting exoplanets, is the bit at the very bottom that's highlighted as slitless spectroscopy. So that takes us all the way from 0.6 microns to about 11 or 12 microns. That's a phenomenal wavelength range compared to what we currently have access to. And it's not only that, it's the fact that James Webb has a 25 square meter primary mirror. That means lots of photons. That means high precision, low noise spectra. And one of the things that James Webb will allow us to do is to access temperate terrestrial exoplanets. This is going to be possible. So possibly a true Earth analog planet could be examined with James Webb. One of the things that we'd like to be able to do is look for ozone. Ozone might be a really good way of identifying another planet similar to the Earth, because ozone is produced from the interaction of ultraviolet photons and molecular oxygen. So it's effectively another way of looking for oxygen. And we can do this with James Webb. So this is a simulated observation. This is what we might be able to do with James Webb. And there's a bump in that transmission spectrum at about 9 microns, and that bump corresponds to ozone. And we've demonstrated that that would be detectable with James Webb if we had a suitable target. It just so happens that we have not just one, but a few suitable targets. This system, called the TRAPPIST-1 system, was detected a few years ago. There are 7 rocky planets orbiting a nice, cool, small star in our near neighbourhood. And that's an ideal set of conditions, because if you want to look at something small planet-wise, you want to look for a small star. You need the habitable zone, the region of space that might allow liquid water to be pretty close to the star, which it would be for a cool star. And you need the star to be nearby so that you get lots of photons. And it turns out that planets E and F in this system are quite possibly about the same temperature as the Earth. So these are some simulated observations of what you might see for TRAPPIST-1e with one of the instruments on James Webb called NIRSPEC. This goes from 1 to 5 microns. So depending on whether the atmosphere is sort of fairly water-rich and has ozone, a bit more like the Earth, those are the blue spectra, or whether it's a bit more like Venus, we should be able to observe it, and we should also be able to distinguish between the two, which is really exciting. So finally, beyond James Webb, we're looking to something that can do a broader characterization of lots of different atmospheres. So the James Webb Space Telescope is going to give us some really exquisite observations of some exoplanets, but it's a general purpose observatory. So it's not going to allow us to seriously populate that diagram, that mass temperature diagram, with any sort of statistical accuracy. But Ariel will do this. So Ariel is a mission that's due to launch in 2029 that I've been very fortunate to be involved in for a number of years. And it aims to characterize the atmospheres of about 1,000 exoplanets. This is well over, at least an order of magnitude more than we're able to do at the moment. And these are some example mock-up spectra of what you might see with Ariel. So you'll notice that you don't get the beautiful precision of James Webb or quite the spectral coverage, but what you do get is the sheer number of targets that can be observed. So that brings me to the end of talking at you. Thank you very much for your attention. Just to conclude, I think you'll agree that we've come a long way in the last 10 years. We've now got a fairly well characterized population of hot Jupiters. We can see things like regime changes as you increase the amount of irradiation and the temperature. We've got some mysteries that we need to solve, like where is all the water gone? We need to try and find a way of seeing through those clouds for the mini Neptunes. Still lots of gaps in the picture that we hope James Webb will be able to at least partially allow us to resolve. Some of those are observational, some of them are theoretical. We are aware that we are observing these planets effectively as single point sources, and we're assuming that the atmosphere is the same everywhere. Of course, that isn't really true, so we need to work out how to reconcile that and try and improve our modelling capacity. And lots of things that we haven't yet been able to explain. So I think if you were to come back for a similar lecture in 10 years' time, the picture will probably have changed an enormous amount.